Hello, everyone. My name is Dr.Sharidya Rahman. So I'm one of the doctoral scholars at Australian National University at the School of Engineering. So today, as part of the conference, we'll be talking about highly enhanced nano-electromechanical systems, or which is more commonly known as the NEMS, and we'll be seeing how they can be applied or their applications in microwave and defense industries. So let's start, and let's just start with some introduction. So NEMS, as we most commonly known and know it as, it's called our nano-electromechanical systems, and they're devices that can integrate electrical and mechanical functions at the nanoscale. Usually NEMS can consist of several different devices. They can be miniaturized electrical and mechanical apparatus, and they can be, for instance, they can be actuators, beams, then they can be sensors, pumps, resonators, and motors. However, essentially, these NEMS convert one form of energy into another, and they can be quickly be converted and conveniently measured. So these devices, for instance, biosensors can be a NEMS, and it is important, and is one important application of biosensors could be to monitor important physiological variables during surgical procedures, such as intracranial pressure, weight load, and strain, etc. Now, there has been several different NEMS devices that has been in existence for a long time, and in each of those NEMS devices have a lot of applications. For instance, let's look at some of the common example of NEMS, which is one of the common example of NEMS being a pressure sensor. So for instance, in this particular work, the authors have devised or fabricated a NEMS pressure sensor, which is basically a bioreabsorbable nanoporous silicon device. And one of the major application of this particular device was reliable assessment of the intracranial pressure in rats. So they choose rats as one of the primary medium for investigation, and they showed that this particular pressure sensor can actually measure full range of pressure from 0 to 70 milligram per mercury. So resistance of the sensing element increased monotonically in a linear manner, and this particular application was found to be very relevant to intracranial monitoring. So this device was also had the advantage to be integrated into a wireless transmission, so that the information could be transmitted into a nearby computer or other devices or any memory storage. So another very common example of NEMS is the graphene resonators. So due to the special properties of integrating electrical and mechanical functionality in the nanoscale, so NEMS plays a very important role in the future of computing and sensing fields. So when the size of the resonator reaches about 100 nanometers, so NEMS can be operated at a very high frequency, which means 100 gigahertz or 1 gigahertz, and it requires very extreme sensitivity. So modern applications in microwave and defense industries requires processing power at very high frequencies with extreme sensitivity. So at present, what we have is silicon and gallium arsenide that are being widely used in NEMS, and which have very high Young's modulus and can be easily be fabricated into planar structures. However, the silicon and gallium arsenide cannot totally satisfy the needs of NEMS. So in order to work around that challenge, researchers have come up with something called graphene resonators, which is essentially a graphene oxide sheet or a nanomembrane that is being suspended or transferred on a etched or suspended membrane. So this is an example of a graphene resonator that has been transferred on a substrate that has been with prefabricated silicon nanopillars. So these nanopillars can be fabricated using nanolithography and optical lithography, and of course the electron evaporation technique. And by using ICP plasma etching, this kind of nanopillars and this kind of holes or pre-patterned substrates can be easily be fabricated. And then using some wet transfer or dry transfer technique, the graphene sheet resonator can be easily be transferred onto this pre-etched substrates. So as a result, this kind of graphene resonators have a very good range of applications, and the performance in terms of high frequency is considerably very large. So another very common NEMS device is the hybrid NEMS, which is actually a different version of the graphene oxide NEMS resonator. So in this case, the graphene oxide sheet has been transferred on top of an etched substrate, and when the graphene is placed in this optical field at nanometer scale, so there will be transductions between nanomotion and optical field due to the strong modification of an emitter's relaxation rate and the light emission. So as a result, by tuning the distance between the graphene resonator and emitters, the emission of frequency could be controlled. So in order to do the measurements, researchers can use confocal microscope and use 532 nanometer as an excitation source. So another very common NEMS, or one of the basic NEMS, is called the transistor, and billions of them transistors can be fabricated into a single integrated chips. So transistors form the fundamental component of several different consumer electronics and many different other industrial electronics as well. So the performance of the transistors actually determines the strength of the operative power of the final product. So it is essentially important to develop this kind of transistors with superior material properties or superior electronic properties so that they can be essentially applied in microwave and defense industries. So this particular figure shows a representative concept of an out-of-plane and in-plane NEMS, which is basically our transistors. So they could be electrostatic or piezoelectric transistors, and they could be integrated into various different electronic circuits, including transistors. However, the current NEMS that are in market can experience some sort of challenges as well. So some of the common challenges being strain-induced lattice mismatch, the negative effects of polarization. Then there could be short channel effects, and there could be significant degradation in frequency response. Then there is also possible to have increase in current collapse effect. So all these challenges can result in compromising the device ability and also reduces the reliability and stability. So due to all these challenges, it is essential to develop this. It is essential to nano engineer this kind of transistors and nanoscale devices or nano electromechanical systems, so that we can have improved transistor properties and they can be effectively applied in microwave and defense industries. Like as you mentioned, those industries require operations at very high frequency, at very high temperature, and with maximum sensitivity and performance. In order to work around this kind of challenge, so we developed or we proposed an high electron mobility transistor structure, and we did this design using Synopsys Centros TCAD, which is basically one of the best platform for commercial modeling of this kind of NEMS structure. So in this particular structure that we proposed, we introduced this kind of graded barrier, and then we also introduced aluminum indium gallium nitride based quaternary back barrier. So this quaternary back barrier allows the demonstration of combined effects of polarization engineering and also greater conduction band offset. Another interesting thing about this quaternary alloy, which is aluminum indium gallium nitride, is that it is suggested as a suitable back barrier material due to its inherent properties of being able to search the conduction band offset of gallium nitride buffer and through positive polarization, and prevents the formation of potential well as well into higher band gap than the gallium nitride one. So in addition to that, this kind of gallium nitride, this kind of back barrier provides an additional degree of freedom and also allows independent control of polarization at the interfaces, and also provides a band offset. In addition, so ultimately, this proposed device that we modeled or that we developed is expected to have higher mobility and satisfactory transport properties. Now, in order to actually show that these properties are actually reliable, and this particular transistor model is reliable and is actually fabricated in experiments, so we did a lot of simulation, and we extracted various transistor properties. For instance, electrical properties and also optical properties. So now let's look into some of the interesting output characteristics of this particular transistor model that we developed. So one of the primary properties of transistor is the output and transfer characteristics, which is basically IDS, IDVD, and IDVG graph. So develop and analyze this voltage and current relation. So 4 levels of gate voltage were applied with steps of 2 volt, and VGS was ranging from -4 volt to 2 volt, and the VDS was ramped from 0 to 50 volt. And this gave us IDS versus VDS. And for the output and for the transfer characteristics, which is basically drain current versus gate voltage, we ramped up the gate voltage from -10 volt to 4 volt at a particular drain bias. So we see that from this particular graph that the DC characteristics is quite enhanced in our model structure. That the maximum drain current saturation can reach up to about 5.5 milliampere per millimeter, which is almost 60% enhancement compared to the conventional part at just 2 volt. And similarly, it goes for the current improvement for the transfer characteristics, which can be supplemented by about 1.8 ampere per millimeter, which is also a significant increase in the maximum current saturation in this kind of transistors. So as we can see that the transistor that we model is significantly showing a very enhanced performance, and that can of course be a very good usage in microwave and defense industries. So self-heating is also an important phenomenon that needs to be taken into account, because it causes a reduction in mobility, leading to a reduction in output current as the operation voltage is increased. So this reduction gives a negative slope to the saturation region of the device DC characteristics. However, as we observed in our figure, that the slope is incremental and saturates eventually in the saturation region, which shows that the increased gain is not actually adversing or showing any adverse effect on the transistors, and the thermal characteristics of this particular device that we modeled is actually remaining is controllable, and as a result it is very good, is very important parameter for future application. So next we extracted further properties, which includes electron density, then electron velocity. You can see that the electron density is of course significantly enhanced, and it's almost about 4 times enhancement in the two-dimensional electron gas density in the channel. And of course, electron velocity is also further increased by about 4 into 10 to the power 19, which is about 18 million electron, 18 million centimeter per second. So this is also so these are also a few of the other properties that are enhanced in this transistor model that we developed. Other few other important properties of transistors being hole density, then the hole velocity, and also electric field. As you can see that the hole density is also extravagantly increased, and also then the hole velocity is also low in this barrier, in the barrier of the transistor model that we developed, and is of course the electric field, which is of course one of the important parameters, is of course significant, and is of course, and however it is a bit non-uniform as well. As witnessed, the large electric field induced in this channel effectively depletes and confines the transport electrons into the 2D EG layer, which is basically this one, and that subsequently suppresses the gate leakage. So gate leakage is of course one of the drawbacks of current transistors. So rising step in the electric potential in the channel therefore also helps to improve the electron velocity, and of course also improves the IV characteristics as well, in addition to having a lower gate leakage current. As mentioned, one of the few of the other important properties that are also enhanced in this transistor model that we developed is the total current density. So this is the conventional one, and this is the transistor model. This is the current density map of the transistor model that we developed. So as you can see that both the buffer and the channel area is experiencing increased density of carrier, and hence the current, and therefore the current when the back barrier is inserted with the barrier grading. This implies that device current handling capabilities is improved, and it can withstand stronger electric field with stronger depletion effect. So this is one of the key parameters in defense and microwave industries. Furthermore, we looked into other channel properties. So by changing the channel length, we looked into its effect into IDVD and IDVG curves. We saw that it doesn't changes the output and DC characteristics much. However, it does have an effect on the threshold voltage as well. In total, so as in summary, in this particular project, we work on the DC analysis of aluminum indium gallium nitride based high electron voltage transistors, and we showed the potential capabilities of this indium technology, and that can be exploited into various applications. And we showed that the particular device that we proposed or modeled has a very enhanced output and transfer characteristics. In addition to that, we also showed that this kind of graded structure and quaternary back barrier can have enhancement of other electronic properties like current density, then the electric field and electron velocity, etc. So, so anyone can have any further reading into this particular paper. So this work was published in ECS Journal of Solid State Science and Technology, and I encourage people to have further reading in this particular journal as well. Thank you everyone for listening, and I hope to answer I'm happy to answer any questions in the future.